Hello again. Tonight we're going to talk about the relationship between vacuum and photons and see if one can affect the other. So we know about the electromagnetic spectrum, light and radio and photons. They would not normally be expected to interact with themselves or with air molecules. You probably have seen a beam of sunlight interacting with dust in the air, but dust is very big and heavy compared with air molecules. But we also know that photons can transfer momentum and affect movement of materials. There was a 2018 Nobel Prize in Physics for optical tweezers. This is where a low power, or I think around 5 milliwatt infrared laser could actually be used to move bacteria across an X-ray microscope stage in vacuum. And I think it actually used 3 of these lasers to nudge in different directions. Bacteria is far heavier and denser than air molecules. If it can move heavier stuff, can it move lighter stuff? And the idea would be that if something's not anchored down or it's not sitting on something resistive, then yeah, light should be able to, if you have enough photons, transferring enough momentum to move it. So if you think of the flux, that's the number of photons as a density in cubic space, let's say millimeters. To move something like gas molecules, if it's possible, you should be able to create a field of photons, a flux of photons, such that air molecules would not be able to pass between them. And you wouldn't need enough energy in the photons to energize or ionize the air molecules. You want just enough to push them around and prevent them from passing through. The proverbial science fiction airlock. I don't think it needs to be a force field, but so first thing you have to understand is what is a photon, and it has the particle wave duality. For ease of doing things, think of it as a sine wave. It has a vertical linear displacement. Horizontally, there is a tilt. There's an angle called the phase that you can have of the wave, but the width of the wave is presumed to have a horizontal distance of 0. So you need to pack them in side by side. The length of the wave is related to its frequency. The height of the wave, how high the peaks are, if it exists as a wave, is related to the amount of energy in the photon. What's typically not discussed regarding photons is that they're non-interacting. They don't interact with each other, and that if you pack them in, how tightly can you pack them? And at what point, when you're packing them, do the ones that are at a different phase angle interact to prevent you from packing them in even tighter? If you can pack them sufficiently tight, can you pack them tighter such that the gas molecules will not go out between them? This would create a photon flux wall resisting movement of air molecules. But you don't want so much energy in it that it'll ionize the air molecules. So now we have to think of sizes and the effects of them. What kind of gas molecules are dominant in the ambient air of the Earth? Nitrogen, oxygen, argon, xenon, etc. And how big those molecules are. And then what is the size of the photon waves and its wavelength to see if it would present any resistance to it or transfer momentum to the air molecules to the point where they won't move within an area. If I change the pressure inside of a fixed chamber, I can change the essentially index of refraction of that chamber. And in doing so, I change the air pressure in there. And at mean sea level, air has an index of refraction of 1.000293, as opposed to a full vacuum, which has a theoretical index of refraction of 1.0. That's how it's scaled. If I decrease the molecular density to somewhere between that, then I can change the index of refraction. But by doing so, would I be bending the light, or would I be compressing or expanding the air molecules? And the idea is, can I affect this such that it will improve my chances of creating this photon flux barrier? Comparative sizes. This has a hidden, how can that be? It's not an incorrect value. I went back and looked. The most dominant thing in the Earth's atmosphere is nitrogen, not oxygen. It's only 20.1%. If you look at the sizes, like 0.36 nanometers, that's fraction of a billionth of a meter. That's one molecule of nitrogen, which is two atoms of nitrogen, like two atoms of oxygen, 346. When you get down to carbon dioxide, it's 240. You can see that the stuff that we don't need for breathing is smaller and smaller and smaller. The two things that we need for respiration, for breathing, are essentially nitrogen and oxygen. So how big are the wavelengths of various photons? And you can see that infrared is very large, 1 million down to 780 nanometers, very wide band. But then as you get to the red, orange, yellow, green, cyan, blue, violet, they get smaller and smaller and smaller. But nowhere do they come close enough to being the size of air molecules until you get down into the X-ray level. And in the X-ray level, it would certainly ionize those molecules and split them apart. Don't want that. We're going to have to think not individual photons affecting molecules, but photons in a dense flux acting as a momentum transfer barrier. The easiest, the kind of like the sweet spot, short, cheap is royal blue, 460 nanometer. Those are those really cheap LEDs. And here's that interesting note. Oxygen, which is two atoms of oxygen making up one molecule, is 0.346 nanometers. That's two atoms of the same element. Carbon dioxide, carbon, and two of oxygen is 0.24 nanometers. Wait a minute. That means that something that has three atoms in it is smaller than something that has two atoms in it. And it has to do with the bonds that the molecules establish. And carbon tends to have shorter bonds and draw things together tighter. If you think of it as if we could create a barrier that would stop oxygen from leaking out, carbon dioxide would leak out. This would be a carbon dioxide permeable air filter or scrubber. Even if this doesn't keep airlocks tight, if all it did was it scrubbed out carbon dioxide from the air, along with a bunch of other lower percentage things, this would be a fairly valuable filter, osmotic filter for air purification. How to remove CO2 from the atmosphere. You just pull it through a field of photons and the oxygen stays behind and the CO2 moves out, and you suck that out and you push it into groundwater or some kind of organic material to make it absorb the CO2. Since it's light, there's no filter backflushing required. So as you can see, air molecules are way smaller than photons. So you want to basically restrict the stuff that we need for breathing. You want those to not move through it. Anything else, you can let those leak out, not a problem. You don't want to ionize them, so you don't want ultraviolet or X-ray. You're going to probably rely upon LED technology because that produces the most photons for the cheapest emitters. Lasers would be another approach, but their beam is relatively small. It's more difficult to fan it out. There are formulas for calculating how much power you get out from individual photons by their wavelength and by how many of them there are. So it determines the density of photons, the flux, how many photons you're going to get per square millimeter per second. Is that sufficient to keep the air molecules in? We don't need to keep all of them in. We just need to block the ones that we need for air, for breathing. Anything that's smaller, those can leak out. Anything that's large that we need for like nitrogen, oxygen, those we want to keep in. Yes, there is actually a chart for how you can take two gamma photons, have them come together, and it will actually produce a quark and anti-quark pair. So two photons go in, no photons come out, but you get two quarks. So light creating matter. We don't want to do this. We don't want energy levels at the gamma level. So how would we go about seeing if this works? If I could create a chamber, that cube has 6 sides to it. If it had 5 sides and the last side, the 6th side, has photons streaming across it, then if I could keep the air or vacuum inside the chamber, that would say that the light barrier, the photons moving across the gap, are actually constraining the air so that it doesn't pass through the barrier. You don't need much force to seal this thing. It's more a matter of how much flux you're generating, and whether you need coherent light, all one phase, or whether you can have a mixture of phases. You can either evacuate the inside of the chamber, or you can put the chamber inside of a vacuum chamber or tank and evacuate it that way. You really just want to see, will air move across this barrier? So you could either use a pump to pump out the chamber, which is a small space, easy enough to do, or you can put the whole thing inside of a vacuum chamber and put air inside the enclosure and see if it leaks out. But if you do that, that means you need lots of LEDs on the inside. All needs to operate on batteries because you're not going to have wires going into your vacuum tank. And any way you have controlling it, your data interfaces have to be wireless because, once again, no wires going into the tank. So here's the use case. Here's the science fiction use case. If you said, I've perfected this technology and I use it for my space airlocks, the proverbial science fiction use case episode where you have a airlock, a shipping, a docking area, docking port that you have an outside heavy door, and then inside that you have this energized field of photons. The first thing you do is you have your outside door closed, the airlock is pressurized. Any crew that's not in spacesuits or any crew that's in a ship that's not yet pressurized has to leave. You seal all your ship doors, you seal the inner door going into your spacecraft. You pressurize any vehicles that are inside the airlock. And now you establish your photon flux airlock door inside the physical door. So you set up the field. How fast you do that, it's a matter of controls, but you set it up, and now you can raise the outside door. And if you raise the outside door, the air inside the airlock should still be there. The airlock will transition as you drop that field from breathable to space normal vacuum. Once the field has been dropped, then things can enter or exit the airlock. If you want to reestablish it, how fast you do that is, again, a matter of photon flux controls, but you establish the field, and then you can close your exterior door. Inside the airlock, you have breathable air at normal air pressure. If you transition the airlock to outside, but you have the field up, you still should have that pressure on in there. The question is, will a flux of photons maintain air pressure against the vacuum? Don't know. Here's a test rig. Not in space, but just a little thing. The sidewalls are microscope glass slide, specimen slide. And you have photon sources on one side at the top. You can see on the right there. And then you have a back wall, which is black to absorb any of the photons that make it across. And then you have an air or vacuum tube that goes in there, so you can adjust the air pressure on the insides. And then on the bottom, you take a Peltier chip, and you can either heat or cool the inside to increase or decrease the air pressure. And then you have the photons, multiple layers of them, going across the opening. And if you establish air on the outside, air on the inside, and then you turn on the photon flux, you should be able to start to evacuate the inner chamber, and the outside air should not be permitted to get in there because the photons keep it from getting in. Or you can use pressure instead of a vacuum and push air into there, and the air pressure should be sustained by the flux of photons reflecting the air molecules. And here's kind of how the emitter would look. They do make very tiny LEDs that are 2 millimeters by 2 millimeters. That's for the entire red, green, blue chip assembly. So you could theoretically make single color or monochromatic LEDs even smaller. And I'll show you the details of those in a moment. The idea would be you have 3 rows of LEDs. You have an upper row and a lower row that are all aligned. And then the middle row is offset to close the gap to make the photon flux denser. Here's one of those red, green, blue chips. The outside of the chip package is 2 millimeters by 2 millimeters. They're so small, they recommend you wave solder them. Don't try and solder them by hand. They're surface mount. They're not plated through hole. They're very small. I have some of them. They normally come on a strip, already soldered in, already ready to go. You just apply data and power, and you can select which of the chips you want to have what color and what brightness level. But I want them packed tighter than that. How big is the actual emitting area? And you can see in the left side there where you see green, red, blue. That's where the LEDs are. And the rest of the package is all of the electronics and connectors and stuff. Very little emission space for a very large package, even though the package is only 2 millimeters by 2 millimeters. So how would we do this with single color or monochromatic LEDs? Same sort of thing. You need small LEDs. You need their emission angle to be narrow, and then you pack them up tightly. and you put them in 3 layers. So here's one blue LED. It's 3.45 by 3.45 millimeters, which is bigger than 2 millimeters by 2 millimeters. But this puts out a lot more photons, and the emission angle is 130 degrees. That would be 90. So it's even brighter than that. But you'll note that the little clear bubble in the center, that's where all the photons come out. But then the package is around the side. So there's a lot of package area that doesn't have photons coming out of it. So that presents a bit of a problem. And then when you solder them down, the little ears stick out on the bottom edge. So there's about 1 millimeter gap you need between the chips. So here's kind of a packing on the right side in that picture, showing you the individual emitters and their little round lens on the top. And then the actual emission, if you were sitting on top of them looking at the emission, that larger circle, the lighter blue circle, would be how you pack them all together. But then I did the calculations of, okay, here's the characteristics of this LED. How many LEDs do I need to get to what density I need in the flux to make sure that oxygen and nitrogen can't pass through it? And it turns out that even at this level, my density is off by about 100,000 times. Yeah, it needs to be packed even denser. And the only way to do that is to make the packages smaller, make the lenses almost vertical, and make the area remaining around the outside edge of the package even tighter. But if I didn't want to do, a little chamber, I wanted to put this inside of a vacuum tank. I have a 5-gallon vacuum tank with a 6 cubic feet per minute vacuum pump. So I have the stuff to do it. I just don't have the LED fabrication to create the emitters. So if we can change the index of refraction of essentially the material inside the chamber by way of heating it or cooling it, or we can block the gases from going through, then we have created something whereby the air won't move through it. And we know that if we have a photon flux, it can transfer momentum as courtesy of the 2018 Nobel Prize in Physics. But can we establish a flux such that it would not be permeable or impermeable to gas molecules that we normally use for respiration, meaning nitrogen and oxygen? All the other stuff can flow through, don't care about it. But given that I have to pack them even tighter than I can do with commercially available products, it's theoretically possible, but I'm not in the packaging industry or the semiconductor LED design industry to do this. Maybe some LED manufacturer will watch this video once I post it publicly and might try it out themselves in their labs. But the idea would be, if you can do this, obviously you can create an airlock, which in the future might be useful on spacecraft. But more importantly, there's a lot of hundreds of millions of dollars going into air scrubbers to remove CO2. And if this can act as an osmotic air scrubber for CO2 that doesn't require periodic cleaning, there could be revenue in that. Or, if you do it right, maybe just a Nobel, or if you're doing airlocks and osmotic scrubbers, then maybe 2 Nobels. All kinds of links. This took like 3 weeks of background effort to pull all this together. Okay. Comments? Question?
I have a question. What is the wavelength of the laser that used for tweezers?
It's an infrared laser. I think it's about, what's double 532? Because I know the output is 532, so it'll be 1,064 nanometers.
Okay, so for the molecules that you're moving a whole bacteria, a whole viruses, so I don't see, like, using the example, maybe you don't have to worry about the wavelength of the light for controlling the motion of the air molecules.
Well, I don't want to push the individual molecules. I want to push a collection of ambient gas molecules. So I need to create not just one point laser source. I need to create a laser field that
a
the
cascade,
molecules will
right?
pass through. Yeah. And to do
Okay,
that, I
so
have to up the flux.
I might have one idea that is kind of silly, but it kind of works. Whenever you go to a store or you go to a Dunkin' Donuts windows, they have like a air conditioner fast flow, like laminar flow.
Yep.
That's they call it air curtain.
Yep.
And that one would be kind of analogous to what you want to do.
Yes. I want a photon air curtain.
Yeah. So read a little bit more how air curtain works, just for you to see the motion of the air being blocked, and like kind of
Well,
have an idea
yeah,
how that works, and might give you some kind of a inspiration for solving the problem.
positive and negative pressures are something that they use in hospitals. If you happen to be in an isolation ward, you want to keep whatever germs are in the isolation ward. So you want a negative air pressure. So if somebody opens the door to walk in, the clean air from the outside gets sucked in when the person comes in the doors, and then the doors shut, and there's a negative pressure inside the unit.
Yeah, and we normally have an airlock when we do that,
Yes, yes,
and you
um,
get scrubbed like twice.
yes, but if you're trying to remove particles from someone, like you're in a semiconductor fabrication lab, you have a positive air pressure. So you go in, you come out of the clean area, and the door closes behind you. And before the door opens on the other side to let you out, high pressure air comes in and blows everything off of you. And then low pressure air sucks that air out. So it sucks all the debris out. And now you can open the inner doors and go out. So positive and negative pressures, certainly in healthcare, is something that I've seen used. The ones that they use at drive up windows are specifically designed to reduce the air conditioning costs. So
Yeah.
the air conditioning is cooler inside the restaurant, and it's under a positive pressure. So the air curtain that they're blowing is ambient air, so it's going to be warmer, but it's higher pressure than the air pressure inside the restaurant. So it literally blows the hot air away from the window opening.
And it doesn't let the cold come
It doesn't
out.
let the cold air out because it's
Yeah, it's
pushed.
basic as a curtain.
Yes, it's an air curtain.
Yeah.
Grocery stores for a while had them, but then they found it was too much of a sociological hazard to certain garments. Um, you could walk through the antechamber of a grocery store, and air would blow up from the bottom, and that would be used. So before the inner doors would open, the air would blow up from the bottom to keep the air conditioning inside the grocery store. They could have just changed it and make it blow down from above, but then that would mess up people's hair. So nowadays they just have two sets of doors, and they just keep a mild pressure difference between the two doors. Yeah, I
Would a
guess.
shuttlecraft be able to fly through your photon barrier without breaking it?
Would what? Yeah,
Would a shuttlecraft?
I've seen those in science fiction movies where they're talking about a energy field, a force field, being the thing that keeps the air in and the vacuum out. There's contours on the outsides of an aircraft that, if the photon flux was of high enough density and the surface was quite reflective, then if you had the photons going just from one side to the other, it wouldn't work because the spacecraft would shut off the photons on the opposite side. You would need
Yeah,
photons coming from all four directions.
yeah.
Yeah. And then it might work.
If you could get that to work, then it's useful. Otherwise, what would be the point of having this on, let's say, a starship
Because
if you couldn't fly through it?
it's far faster to turn off a field of photons than it is to raise a big heavy metal door.
Oh, good point.
Yeah. Far faster to open it and to close it.
Hmm.
So that's why, if you want to start doing your space work, first thing you do is turn on the field and then open the outer door. That takes time. But when you finally want to leave, everybody leaves the room, everybody gets in the ships get prepared for launch, and then you just drop the field and out you go. Now, the fact that it's higher pressure inside the airlock than outside may actually eject your ship from the
Yeah.
airlock. It's an explosion, it's not an implosion.
Mm.
But now when you're coming back in, the airlock would be vacuum, and you'd have to have it come in and then establish the field, pump the air in, and now before you start closing the big metal door, you have a place where you can work.
Mhm.
It's just a thought.
It's fun. It's fun to think about it.
And
I'm
I
already
was
here thinking about air curtains and stuff. Yeah.
I was seriously thinking of doing it until I found out that my flux density would be about 1000x off. And I said, well, I'm not going to create any new LEDs anytime soon. Now, if it was just packing the surface mount LEDs tighter, I could probably cobble something together. But it's the fact that the packages, even at 2 millimeters, the lens on the top doesn't go all the way to the edges. There's a gap. And then there's a gap where you have to solder them down. So the gap from the center of one lens to the center of another lens is a good portion of the total diameter of the lens. It's going to be letting things through there that otherwise you.
Maybe just for fun, if you could put something like, like those smoke makers, you could make something smoke inside the box and try to see if you can slow down the smoke come out.
The 2 by 2 millimeter surface mount LEDs could probably stop smoke particles from getting out, because smoke particles people think of as small. But I remember back in the days of moving head disk drives, when we had like the giant 14-inch platter multi-stack disk drives, the 3330s and such, 3380s. And we always had this diagram that we would scare software developers and hardware engineers with. Here's the size of a human hair. Here's the size of a smoke particle. Here's the height of a thumbprint, to say, and here's where the moving heads fly. And they're always like a fraction of that distance. So a smoke particle was this giant looking piece of steel wool compared to the flying height of the disk drive. So yeah, I think it probably could keep smoke in. That would be interesting to do that. Okay, you've reignited me. We'll come back in another few weeks and I'll have done something, because I already
talk to Casinos about that.
I already have the microscope slides, so I've got the glass slides for it.
Yeah, it was like a silly idea to try out. If you can stop
silly.
Smoke,
it's not silly. It's demonstrative and analogous.
Yeah. Yeah, like while you're explaining, the first thing came was the Dunkin' Donuts windows. Whenever I have to go to the museum very early, I don't have energy to make breakfast. I barely, have time to shower, because I'm not waking up at 4 a.m. I'm waking at 5. And so I'm like, nah, breakfast or Dunkin' Donuts.
Here's the connect the dots. Let's say I can create a photon flux that will keep smoke particles out. How would that be useful?
Oh, so anti-pollution.
No.
Filtration.
Think life safety. Firefighters, they have to wear these masks that have the big filters, and the filters are so restrictive that it actually hurts their breathing, because they have to suck hard to get air in. Well, if they had
carrying heavy equipment in the heat,
they have to carry a heavy oxygen tank. If instead they had light filters that would keep the smoke out but allow air to pass through, that would be something interesting.
Yeah. Well, play with smoke first, because it's visible, larger particles.
Yes.
They're colloid.
Yes.
They have Brownian movement. It's kind of, you can play with that.
Well, if a 5 milliwatt laser can push around a bacteria on an X-ray microscope slide, a couple of milliwatts of just LED power would certainly be able to move a smoke particle, just like light from the sun in a well-lit room can disturb dust particles.
Yeah.
Interesting. I like that.
I guess I'm in the right place.
I appreciate you being here.
Yeah, no. I mean, I work in the right place, like making small models of larger things for kids to understand science.
Mhm.
I guess I'm useful.
Never doubt that. Okay. Any other comments or questions before I stop recording? Hearing nothing.